Light basics and the index of refraction. The spectrum of visible light is around 400 to 700 nanometers, where a nanometer is 10 to the minus ninth meters. Violet light has the smallest wavelength, while red has the largest. White light is the combination of all the wavelengths of light in the visible spectrum. Light travels through a vacuum at the speed of light, c. The speed of light is 3 times 10 to the 8th meters per second. In all other media, such as water, plastic, glass, etc., the effective speed of light is smaller. Every medium has an index of refraction, n, that indicates the effective speed of light inside the material, which we call v, relative to the speed of light in a vacuum. c is equal to 3 times 10 to the 8th meters per second. So n will always be greater than 1 because c will always be greater than v. As light travels between media, for example if it goes from air to water, or vice versa, the frequency f of the light remains the same. That's important. Frequency stays constant. If not, then the waves would build up on the interface, which doesn't happen. The wavelength of the light will change in the different media. Using the formula, frequency is velocity over lambda, and the definition of n, we obtain another expression for the index of refraction. We have n is equal to c over v in the media that we're looking at. We replace c with f times the wavelength of light in a vacuum. Then below that we have frequency times the wavelength of light in the medium. The f's cancel out because they're the same, the frequency is the same. So another expression for the index of refraction is the wavelength of light in a vacuum divided by the wavelength of light in the medium. The index of refraction also tells us how much the light bends, which is another name for refraction, or refraction is another name for light bending, when moving between the media. The light rays bend towards the normal when traveling into a medium with a greater index of refraction, and they bend away from the normal when traveling into a medium with a smaller index of refraction. So the key on this is to first draw your normal line, which is perpendicular to your interface. That's what normal means. And then here we have an incident light ray. It goes from air to water. Water has a higher index of refraction, so this refracted ray here, hopefully you can see how that bends towards the normal. And here's your reflected ray. And by the way, that's the same angle as the angle of incidence. And let's take another case where we come up from the water. In this case, it's going to an index of refraction that's smaller, so it bends away from the normal line. The index of refraction in air only varies slightly from the index of refraction in a vacuum. That enables us to use the speed of light, 3 times 8 meters per second, as a good approximation of the speed of light in air. So let's find the index of refraction for air or a vacuum. It will be c over v, but v is approximately equal to c, so n is c over c, n is equal to 1. The index of refraction for air, and of course a vacuum then, is 1. All other materials have higher indices of refraction.